So this is an explanation for a week 7 homework 1, but this basically covers the content that we went over in the class last week and kind of expands on it. So this is the homework file, week 7 homework 1. There are 5 sections. So the top one being section 1, section 2, section 3, section 4, section 5. So for each section I put a example on the left side, which is what I'm going to explain in this video, and the question that's in the Google form is a variation of that example. So if you follow step by step what's in the example and understand it, then you should be able to solve the questions on your own. Okay, so let's start with section 1, example number 1. So first of all, here's so basically what's happening is, imagine two poles that's supporting a cable, and in the middle of the cable there's a 200-pound force weight hanging there. So the cable is taking this shape, and we are already defining that the actual shape of the cable that is going to take. This is pretty simple. So it's gonna sag down 2 feet deep, and yeah, so basically we want to determine what the internal force of this cable is. In this case it's pretty obvious that it's in tension because it's a cable that's sagging down. So yeah, let's just assume that that's in tension. The fundamental information such as force scale is shown here. So here I'm representing 200-pound force with a line that is 20 inches long. Therefore the force scale being 1 inch equals 10-pound force. Alright, so now we want to start with something that is called loading diagram, which where we will show this horizontal line at the same distance apart as I'm showing here. So it's 10 feet apart. So it's a 10 feet long horizontal line. In the middle of it, 5 feet, 5 feet, we have a downward vertical load of 200-pound force working. So that's in the middle. And I guess once we get to the beam examples, we're gonna talk about the reactions, but you know, something needs to be supporting each end of this pole to hold the cables up. So we just and you know, since it's completely symmetrical, let's just say that it's two upward 100-pound force that's pushing up. Anyways, first step is to label areas that's between the forces. So there is obviously one upward force here, downward force here, there's another upward force here. So we will call this zone, which is in between we'll kind of follow the clockwise notation system. So the A is between that reaction on the left side and load in the middle. And the next zone is called B, which is between this and that. And then the last one being underneath this horizontal line, which is the area C, which is between this 100-pound force and 100-pound force. So in this case, it's the form of the cable is already kind of defined and it's pretty obvious. So we can actually start drawing a diagram that looks like that directly, but let's just pretend that we don't know the shape of the cable that is going to take for now, and then later kind of draw what's shown on that left side like this. So As always, we have to start a force diagram based on this loading diagram. So we start by mapping the force that's on the loading diagram. So we'll start by mapping this force, this vertical force, and we will call it AB, since it's a force that's starting at so since it's a force that's lying between zone A and B on the force diagram, it's going to be called AB, and it's going to start from point A and ends at point B. So now what we're going to do is we're going to pick a random point, actually anywhere on outside of this line, to start our diagram. But for now we're going to put it on the right side, and I'm going to call it temporary P, because we are going to have to adjust the location of this point P to its final location. But the first thing I'm going to do is I'm going to connect the point A to temporary point P. Same thing, point B to temporary point P. Let's just match the color by doing match properties. And I'm gonna start drawing the one configuration of the form that a funicular cable can take with this type of load back onto the loading diagram. So I simply locate this diagonal line, which is purple, which is the point line AP, in the zone that's signified by alphabet A. So this line should span between these two vertical lines. Next one is going to be here. Right, so now we have these two lines connected with each other. What we need also is a closing line that closes these two lines into a closed polygon, and that's corresponding to zone C. So I'm going to color it with the color of the alphabet C, and that actually determines the location of point C on the force diagram, which also means this determines actually the magnitude of these vertical reactions. So in this case, because it was completely symmetrical, we just assumed that we know them, and it's very easy to guess, but this is how we would, so that reaction on the right side would be called force BC, and that would be a arrow that starts from point B and ends at point C. The reaction on the left side would be a force that starts from point C and ends at point A. So right now, if you compare what we just drew as a form of the cable, which would be this, to what we are asking to do, which is sort of like held by these poles that are same height. On the diagram that we drew, the height of the left point and the right point is different, whereas this one has two of them at the same height. So we can modify these diagrams to match what's on here by simply copying the geometry and basically modifying the diagram to match what's here. So our force polygon, instead of looking like this, it should look like that, which match exactly the form of the cable. And if I zoom in, so what I need to do is to modify this force diagram and position of point P to match this force polygon. So how do we do that? So we know this green line, let's just so we know this green line was supposed to be this horizontal line, so we can anchor that to point C where it's supposed to be on this part of the diagram, as well as we can copy the purple line to point A. So now what we know is instead of point P being here, it should have been at the intersection of these two lines. So we can move this entire point by turning on the edit points. Let's grab this point and move from here to that intersection point. And let's call this point P. So now we have the force diagram that completely matches our force polygon here as well, right? So the lines, two lines are parallel, and the top closing line is horizontal. So basically that is the force diagram that's representing the force of the cables that's in here. So to determine the internal force of each of these cables that's on the left and on the right side, we can simply measure the length of this line. So if you type in length, it's 26.9 inches, and the force scale that we are using is 1 inch equal 10 pound. So it should be 269.3 pound. So that's in this cable. This line BP, the length is actually the same because it's symmetrical. So this one also has the internal force of 269.3 pounds. So therefore we can say that the tension in this cable, respectively, they're both 269.3 pounds, 269.3 pounds. So example number 2 in section 1. So what if the cable sagged down deeper? So before we were looking at 2 feet deep, so now it's sagging down 4 feet deep. So again, in this case it's fairly simple. We could actually use the diagram that we just drew for the example 1 as a placeholder and compare the difference and modify that diagram. So you can see how these two lines, it's supposed to be deeper as shown here. So the force polygon should actually look like this. And the force diagram should also be changed to reflect these angles. So what you know is that the angles of the purple line and the blue line has changed. It became steeper. So as you can see, if you anchor these two lines to point A and point B, now you know it's supposed to be here and here. And point P should move here. The horizontal line is here. and I'm just gonna show the original diagram as a comparison so you can see how it got shrunk on towards X direction. So now the internal forces of each of these cables can now be determined by getting the length of line AP, which is 16.00 inches. So I'm gonna say that's 160 pounds. Same thing on the right side, same length, so it's also 160 pounds. So that's the tension in these two cables. And what's important is that if you compare the number 1 and number 2, you can see how deeper one, if this funicular form sags down deeper, then the internal force in each of these cables are significantly smaller than if it were shallower. So the thing is, the closer you get to vertical line, you have less force in these cables, and closer you get to the horizontal line like that, you would have more forces. Okay, so this is section 2, example 1. So now we have two vertical loads hanging from the cable. So for example 1, we still have the symmetrical loading and the same height on two ends, on the right and left. So again, yeah, I'm asking to identify the internal forces in each cable, which actually the answer is here. Again, we're going to start from a force diagram with temporary point, and then we're going to adjust the location of point P to draw the accurate force diagram and then determine the answers. So again, we're going to start from the loading diagram, and here I mapped the horizontal lines and two forces equally spaced and two reactions. And we'll start by labeling these areas between the forces, and let's just extend these lines of action so that we can deal with the force polygons later. Again, so yes, we're gonna start drawing the force diagram by mapping all of the vertical forces that's on here on the loading diagram. So the first vertical force that's here, which is between A and B, starts from point A, ends at point B. And then map the next vertical force, which is between B and C, so it's going to start from point B and ends at point C. And then we are going to arbitrarily pick a point P, knowing that we're going to have to adjust that location, so I'm going to call it P temporary. Then we're gonna connect the temporary point P to point A, point B, and point C. Now we are going to start constructing the force polygons underneath the loading diagram. So zone A, which is between these two lines, corresponds to that line A. Line BP is this blue one, corresponding to this zone, which is the blue. And then the last one is CP. Let me adjust its location a little bit. So now we have these three lines showing this funicular curve. And we also need to close this force polygon. So I'm going to draw this closing line. And that closing line is what determines the reactions on two sides, vertical reactions. But in this case it was completely symmetrical, so and that the intersection between this closing line and the vertical lines here will be point D. So it should be actually this color, just to clarify. And the point D should be there, but it happens to be identical to point B, so I'm just going to call that point B and D. So after completing this force diagram and force polygon, we know we can see how the form is completely different from what we intended to be. So we need to adjust this diagram. So we intend, first of all, the first portion of the curve to be at this angle because it's 4 feet deep and 3 feet 4 inches wide. So that's the angle that we want it to take. And we also know that closing line of this force polygon needs to be horizontal. So from these two pieces of information, we should be able to determine how to modify this force diagram. So this line here is what needs to pass through point A and point P, and that yellow line here is something that should pass through point D and point P. I'm going to copy from here to here. So therefore we know the point P needs to be there. I can simply draw these here, but let me just grab all of these. So now point P, instead of being there, it should move to that location. And instead of calling it point P temp, I'm going to call it point P. And let's complete the diagram. So the blue needs to be at the bottom, and the green is on the right side, and it's symmetrical as well. Anyway, so this is the funicular curve that the cable should take given those lows and the initial condition that we set on the left side. So now what I'm asking in the question is to identify the internal forces of each of these cables, so that you can simply get it by measuring the lengths of these curves. So that purple portion is 26.03. So the force scale that we are using is 1 inch equal 10 pounds as everything else. So let's just call it 260.3. It's right here. And then the blue cable is 16.667 inches. So let's call it 166.7 pound force. And this one, it's the same length as the purple portion, so the internal force in the cable should be the same too. So the tensile forces in these cables are as shown in here. So yes, this would be the resulting diagram of the cable taking this shape, and internal forces are as shown, and these are the applied loads. So section 2, example 2. So here the only difference is I'm lifting up the right end of the cable 2 feet higher because it's 8 feet instead of 6 feet. Again, we're gonna follow the same exact steps to determine the internal forces as well as the correct shape of the funicular curve. So this time we know that the right end is 2 feet higher, but since it's not completely symmetrical now, so we don't necessarily know the correct angles for these two cables. So these are kind of drawn diagrammatically, but they are not precise. One thing we're setting though is that this first point, that the left side, the first weight that's hanging on the left side, at that point the cable is 2 feet above the ground. So we know the angle of this first portion of the cable because we know the horizontal distance to the point as well as the vertical distance to the point. So that's one piece of information that we know. And for the force diagram, I'm just showing the same exact diagram as we drew in the previous example. Let me just trim that portion, which we know for sure that it's not going to match what's on here, but this is what we've used before. So I'm going to use this as a temporary diagram from which I'll make an adjustment and to match what's in here. So that's the force diagram and that's the force polygon, and two things that we know we need to adjust, right? So that closing line, because we lifted the one end 2 feet up, so now that used to be a horizontal line, but now it's this sort of like upward diagonal line. Another thing we know is this first segment of this funicular curve is fixed, so that's something that we can use. So then, again, following the same process, I'm going to copy that part of that force diagram. So what we know is the purple portion is something that should pass through point A and point P, and that closing line is something that should pass through point D and point P. So now from these two lines we can actually determine where the point P should be, which is at that intersection. So I'm gonna call that point P, and because of that we know where so now we can connect point P with all the other points, sorry. So each of these three segments are already identified. So that portion is PB is what should match what's in the area B. So I'm going to anchor that to the endpoint of the first line. And then that last segment of the funicular curve is that line CP. And we have this closed polygon, so we know that this diagram is correct. So basically this is the shape that the cable should take. And we can already identify the internal forces by getting the length again. Applying the force scale, so 22.3, which should be something like, anyway, so let's keep getting the lengths. So the first one was 22.315, second one was 14.5, third line is 26.954. So based on this inches and applying the force scale, 1 inch equal 10 pound force. So by getting the lengths as shown here of these lines in the force diagram and applying the force scale of 1 inch equal 10 pound force, that's the internal force that we get on here. So this is the complete diagram of the cable, hanging cable, showing the internal tensile force, applied load, height of that second point on the right, which is 32 inches above, and yeah, so on and so forth. So for the homework questions, you should be able to apply the same exact method and identify the internal forces Q3, Q4, Q5, as well as the height of the point on the second load. Okay, so this is section 3, example 1. So what's different for section 3 is not only that there's a fact that there are 3 points where the loads are hanging from, but also we are, so in the section 2 we were locking the part of the geometry to a specific angle and then try to derive the form from there. But here what I'm asking is that we are setting the internal force, actually the maximum internal force of all of the cable to be at 500 pound force, and depending on which we are going to define the geometry. So yeah, so that's what we are going to do. And here's the steps again, but we're gonna again start from the temporary diagram and adjust it to the correct diagram. So again, we're gonna start from the loading diagram. We're gonna name the areas alphabetically. We'll draw these lines. So first we're gonna map all of the vertical forces, which is, first one is AB, which is this. Next one is BC. Next one being CD, right? And then we are going to locate arbitrarily the temporary point P. And we are going to connect temporary point P to point A, B, C, and D. We're going to start mapping it onto a force polygon underneath the loading diagram. So this being the parallel line between these two, which is A zone, blue line in the B area, line PC in the C area, and line PD in the D area. And now we are going to have to close this line, which corresponds to this zone E, which is underneath this horizontal line, which is going to determine the location of point E on the force diagram, which also incidentally identifies the vertical reactions, which isn't important in here, but in the beam examples we are going to deal with it a lot. Anyway, so what we want to do now is again use some of the criteria that's given here on the left side in order to modify this temporary force diagram and force polygon to match what we need. So first thing we know is that these two endpoints of these funicular curves are on the same exact height, so we know that the top closing line should be a horizontal line. So I'm going to move this here. So this line, which is the closing line here, should pass through point E, as well as it should pass through point P. So point P will be somewhere along this line, which we don't know where yet. So the next criteria that we have, like I said in the beginning, it's about the internal force in all of the cables. So we need to keep the maximum tensile force in the cable at 500 pound force. So let's just look at whatever we draw above and what the internal forces are in this case. That is, if that cable takes that shape, right? So I measured the lengths of all of these lines in this temporary force diagram, and it says 63, 64, 71, 83. So I can tell currently the maximum internal force in the cable, applying the force scale of 1 inch and 10 pound force. The maximum force is right here, which is something like 830 pound force, which is above we can have, which is 500. So what we know is point P is going to be somewhere, and we are going to be connecting point A, B, C, D to this point. And basically we need to keep the maximum at 500, which is in this force scale that's equal to 50 inches. So what I'm gonna do is, in order for me to make sure that this line is 500 pound or 50 inches, I need to draw a circle whose radius is 50 inches. I need to also do it from point D, because the potential line, whichever one that can be the longest line from in. So in this diagram, what could be the longest line is either the bottom one or the top one. In this case, actually, because it's completely symmetrical, these two are equally long. Currently this is 67, the middle one is 60.8, and so the top one and bottom one is at 67 inches, which is too long. So in order for these to be below 50, I drew this circle at radius 50. So it's basically the point P needs to be at the intersection of this circle and that horizontal line. So let's make an intersection. So the point P needs to be located there, which actually helps us guarantee now, if I connect, let me delete these circles. If I connect these 2 points, the length of that line is 50 inches. Keep drawing these lines. So that's where point P needs to be, and these are the angles that the cables need to take. So going back to the fourth polygon that we were constructing, I'm going to now locate them in the diagram. So that's the form, the funicular form of this cable. So put in the context, so this would be the cable under this loading, given the condition that the internal force in the maximum internal force being 500 pound. So the height of this is at 42 inches. Okay, so this is example 2 of section 3. So the only difference between this and section 1 is on the right hand side it's lower, and also the maximum tensile force is now 750 instead of 500. So again, starting from this temporary diagram, two things that are different for sure is the top, the closing line is now it's sloped, so I'm gonna copy it here, so that's different, and also the angle of the first line will probably change, but we don't know yet. So let me copy these forces down first, right? All right, so now, so that's the closing line, so that's what we know as this yellow line, so I'm gonna copy that here. And again, it can be very quick, so basically the wherever the point P is, it will be on here, and we will be connecting point P to point A, B, C, D, right? And whatever the longest line cannot be longer than 75 inches. That is using the force scale again, right? Because we're referring to this force scale, 1 inch equal 10 pound force. So let's do 75 from one end and another end. So whatever is shorter would be the governing rule. So let me delete all these first. So intersection between the circle that I drew from point A and this diagonal line, and then the circle that I drew from point D and that diagonal line. And apparently the one from point A is closer, so that would be a limiting factor. So I'm gonna delete this. I'm going to delete this circle, and if I connect this new point P and point A, B, C, D, the lines of each of these lines, the lengths of each of these lines would be 75, 64, 58, and dp, so that the longest one is guaranteed to be 75. So this is the correct geometry. If we have used another line, obviously all of these lines would get longer than 70. I mean, the maximum would get longer than 75, so that is not good. So let's just copy these geometries back into the force polygon. So this would be the correct force polygon for the given condition. So again, if I map that the funicular curve back into this drawing, this would be the shape that the cable is going to take, and the dimension from the bottom would be whatever that is, right, for these 2 points. So again, For the questions, section 3 questions, it's pretty much exactly the same, except that each load is now 300 pounds, and some of the condition, the maximum tensile force for number 1 is 900 pounds, and for the second problem, I guess the height is slightly different, and also the load is different, and also the maximum tensile force is slightly different. Okay, so this is section 4, example 1. Again, similar problem. We have more loads now, 1, 2, 3, 4, 5 loads hanging from the cable. What's different this time is we are setting the geometry, in a sense, for the cable, but really we are determining the geometry of the funicular curve by saying that the cable will pass through point 1, point 2, and point 3. Point 1 and point 2 are two endpoints, so that's kind of obvious, but point 3 is, if you look at it closer, is a point where the second from the right load is hanging from, which should be at 3 feet above the ground. So that's really how the point 3 is determined. It's possible to actually draw a funicular curve by defining 3 points. So that's what we are going to do. And just going back to the question, what the question is asking for is to determine the height of the lowest point of the cable based on the geometry that we're using. So again, we are going to start from the temporary diagram and adjust the geometry. So same as always, naming all of the areas A, B, C, D, E, F, G, mapping all of the vertical forces. So first one being AB, next one is BC, next one is CD, DE, EF. So that's all of the downward vertical forces. And then you're going to locate a temporary P point at any arbitrary location, and you start connecting point A, B, C, D, E, F to that temporary point to complete this diagram. Now you're gonna start locating the line segments PA, PB, PC as shown here, so that it corresponds to the areas that's shown above, and this has to be a closed polygon. So now this closing line, which corresponds to the zone G, would be complete the force polygon, and now you transfer that closing line to point P, which is a temporary one, and the intersection between the vertical lines here and that diagonal line determines the location of point G, which then determines the location of the magnitude of these two reactions on the two sides, vertical reactions. So that's the temporary force diagram and force polygons. So now there's another important piece of information, which is this one, which is connecting P1 and P3. So this funicular curve, that's kind of, so this is not a correct funicular curve, but I'm guessing it's gonna look something like that, right? So assuming, so anyway, so it's gonna have to look something like this, and what we know is that, again, the closing line is going to be horizontal, but another thing that we know is this line right here that connects P1 and P3 is also kind of fixed. So in this case, this is gonna go from the leftmost point to 1, 2, 3, 4th vertical line. So that's actually another kind of a fixed line or geometry. And obviously that I just manually drew them, so that's not going to be right. But this is kind of important thing. So anyway, so the top closing line needs to change to horizontal. So that's something that we know. So it needs to be changed to horizontal. So the point P would be somewhere along this horizontal line. So that's good. Another line here, that's basically if you, so this is what's connecting the left end to that point right here, which is intersection between the funicular curve and this vertical line. So basically this has to change to this, and what corresponds to this that we know as a fixed geometry on the left hand side in the diagram that we don't see right now is what corresponds to this. So let's just forget about these for now. So basically this needs to change to this, and that needs to change to that. So we're gonna use this temporary line that connects this point and this point, and we're gonna map it back to temporary point P. We're gonna get the intersection of these vertical lines and this new diagonal line that's here, and call that point X. So now what we know is the fourth polygon that we have here needs to change to something like this. Out of this, what we know for sure is the geometry of the closing line and that line, right? So here's how we are going to change. So first of all, the closing line that's going to pass through point G has to be horizontal. So point P would be on this point somewhere. Another thing that we know is this gray line that's shown here now needs to change the angle to be same as this guy. So we are going to copy that to point X. So the new point P would be determined by the intersection of these two lines. So that's actually the new point P. So now the entire diagram should be modified to so that the point P is right there. So now the entire geometry of this fourth diagram should be modified so that the point P is right here. So everything is going to that point P. So this is our new fourth diagram. So let me delete the temporary one. And we know that line and that line is correct. But now we're gonna start mapping these back onto the fourth polygon. A, B, C, D. As you can see, D passes through the point that was defined by this line, and then another line, E, F. So trim everything. So that's the new funicular curve. So if you map that funicular curve back into the diagram, this is what you see. Again, this funicular curve is passing through point 3, so that we're good. It's symmetrical because 2 points are at the same height and all the lows are equal. I think what I was asking was the lowest point, so in this case it's 31.5 inches from the ground. So example 2 is also pretty much the same, except for the right hand side. The point is now raised 3 feet higher, so this is point 2 is now at 9 feet above the ground. So again, I guess I would use the force diagram that I just created for the previous example and use that as a temporary diagram to modify to meet the criteria that I'm setting here. Alright, so I guess I didn't bother drawing a temporary, the bogus funicular curve, but it's supposed to be, no, that's not really right, but it should look like something like this. Yeah. Because the right hand is raised, but what's really important is the two endpoints, P1 and P2, and it actually passes through P3. So that's how P3 is defined, by being the same way as the last one. So this line that connects P1 and P2 and this line that connects P2 and P1 and P3 is important. So here's what I have. So I just deleted the completed force diagram and force polygon, but here's this is a temporary version and it's different from what we should have. So I just copied this 2 pieces of information that we know for sure from this geometry diagram on the left side. So this one needs to be the closing line, right? And then this one needs to be a whatever that line which connects the point here and point here, which is along this line on the force load line of action. So now I am going to copy these vertical forces that's already mapped. So point X actually doesn't move either because the criteria hasn't changed. So anyway, so again, the same thing. This needs to be the closing line, so it should pass through point G, and this should pass through point X. And now that is going to determine our new point P. So anyway, so this should be the new point P, and if you connect point P to all of the points, this is a new force diagram that you should get, and you can construct the force polygon based on that one. F. So yeah, that's the new force polygon based on the criteria. And this is what it looks like when it's mapped to the context. And so the bottom point, the lowest point, is actually 22.5 inches above the ground. Okay, so last one is section 5. There's only one example in section 5. So really, the biggest difference is that now it used to be, so all of the other problems had a uniform, same load everywhere, but now we have 1, 2, 3, 4, 5 points that the lows are hanging from, and each lows are completely different. So from the left side 500, 400 all the way down to 100. So that's the biggest difference, and we are fixing the first segment of this funicular curve by fixing its angle, right? So the end point and the beginning, the start point and end point is fixed, so P1 and P3. Anyway, so that's the fixed geometry here. That portion is fixed. So that's basically it. So again, we start from the loading diagram. So that's a 10 feet wide horizontal line. So again, the different thing is that it's the magnitude of the applied load varies from left to right. So therefore, right now we don't really know what the vertical reactions are. Keep going. We're gonna label all of these zones between the forces. And now we are going to map all the vertical forces. So starting with the 500 one, which is between A, B. Next 400 one, which is between B and C, right? So next one is 300 between C and D. Next one is the 200 between D and E. Last one is this 100, you can't really see, 100 between E and F. And then we're gonna pick a, again, random arbitrary temporary P point, and you're gonna connect all of these temporary point to all of these points from A to F. Now you can start mapping the force polygon on the left side. So this is what you get. Then we can now identify the closing line, which should be here. That should be identified with G. So therefore the line, if you copy this line to point P, the intersection between that line and these vertical forces would determine where point G is. It happens to be really close to where point C is, so it's really a little bit hard to see, but it's right there. Now, just a little bit hard to see, so I'm gonna pull it to the side. So that's actually these two, the point G will determine the magnitude of these two vertical reactions. So first one being FG, which is on the right side because it's F going around and going to the G, and next one is GA, which is this one. Okay. So now we drew this temporary force diagram, force polygon, but that's obviously different from what we want. So we want the top closing line to be horizontal because we are holding it at the same height, as well as we want the first curve to be first segment of that funicular curve to be at that angle. So I'm gonna copy that to here, and this is what we want it as the horizontal line is what we want as the closing line. So we want to modify the force diagrams according to this criteria. So now I need to copy this closing line, which defines the zone G to point G, which is right here. It's slightly off of point C, so be careful. And the first line segment gets anchored to point A. So if you get the intersection between these two, that should be the new point P, or the correct location for point P. So now that we determine the new location for point P, we can connect all of the points and basically map it on the false polygon. So it should be this and that one. These two are parallel, these two are parallel, and it's gonna, so this is a new funicular curve that we need. So again, this is a funicular curve that's placed in the context, and what you should notice, it's very slight, so it's a little bit hard to see, but you know, this funicular curve now, because of this asymmetrical loading, the form of this funicular curve is actually not symmetrical either. As you can see, the height of these points respectively are like 54, ever so slightly different, 58.036, 64.364, so on and so forth. So just to prove that it's not symmetrical, I'm going to mirror this shape and see how, yes, they're not symmetrical. And actually, you know, the left hand side is sagging down deeper, which makes sense, right? Because you have more load on the left side, and it gets, you know, it sags shallower as you go to the right side. So so that's example 1 for section 5.